So welcome to the afternoon session, and our first speaker will be Daniel Greb, who will speak on deforming twistor spaces and cycles in the K3 period domain.
Yes, thanks a lot for the introduction and also to the organizers for the invitation to come here. It really gives me great pleasure to be invited and actually take part in this Twistor conference. So I first heard this word maybe 20 years ago when I was a master student at Universität. John Wansley explained to me a little bit. I was not doing it at the time. And then maybe 10 years ago I learned something from Andrew Dancer about the work of Penrose, which really was a big revelation for me because somehow it translated something that I had been thinking about on the holomorphic side into differential geometry, and then it took another 10 years for this idea to take somehow more concrete shape and actually to be transformed into some mathematics, and I will talk about that today. So everything will take place in the realm of K3 surfaces, so these are or compact, say K3 manifold. So for a complex geometer, K3 surface is a compact scalar surface which is simply connected, and it has a holomorphic symplectic form. Yeah, so the H0, so the sections of the holomorphic two-form bundle is generated by one form, and it's everywhere non-degenerate. And so examples are easy to come by. As an algebraic geometer, you write down the general quartic polynomial, homogeneous polynomial, and look at the solution set in P3. It will be an example. Others are Coma surfaces, which show you that not all of these are projective, so not all of them are algebraic. So for this, you take a complex two torus, say product of two elliptic curves. You take the involution given by plus minus 1, since this is a group. Yeah? A torus is a group, you can map a point to its negative. The quotient will look roughly like this. So maybe like a singular quartic surface, you will have 16 cone-type singularities, which you can blow up, and then you get a smooth manifold, which is a K3 surface. So then you can deform the complex structure using deformation theory. And essentially that's all there is, but you already see that you have a lot of examples just after like 2 minutes. So the main game is to understand all of them at the same time. So as a now maybe algebraic geometer, you like I like moduli spaces, so you try to write down a space with a family over it where each member of the family is a K3 surface. And so maybe I just explain the connection to hyperkähler geometry, which is given by Yau's solution of the Calabi conjecture. So you take a Kähler class on your compact complex surface, which is Kähler, so such a class exists. So this is the class of a Kähler form into, let's say, in H2. For example, on the quartic surface in P3, you take the cohomology class of a hyperplane section. Yeah, the hyperplane section will be a curve or Riemann surface on your complex surface, and that will have a cohomology class, and that's a Kähler class because it's given by intersecting with a hyperplane in projective space. And then the Calabi problem asks for the existence of a hyperkähler metric in this class, and the solution by Yau is the following. There exists a unique hyperkähler metric on the underlying real 4 manifold of your compact complex surface with the two properties that one of the G parallel complex structures, maybe J, is the one that you already were considering when you consider this X as a compact complex surface. And then the associated two form associated to your metric is closed, and it has the cohomology class you started with. Yeah, so you can fix the cohomology class, and you can produce a hyperkähler metric unique in that class, and that's a perfect representative of the class. This is maybe how people see it on the one side. On the other hand, you can just use this theorem to produce hyperkähler structures on a compact 4 manifold, which is rare. Yeah? And so this is why you might like K3 surfaces. Yeah. Conversely, you can also start with any compact Riemannian 4 manifold with holonomy SP1 or SU2. which admits, then this will admit a G parallel J such that Mj is actually a K3 surface. So talking about compact Riemannian manifolds with polynomial SP1 or complex K3 surfaces, with this translation it's the same. But the point is that you see here above, if you have one complex structure, say J, then for any Kähler class, okay, you can ask yourself how many are there, you get a hyperkähler structure where this J appears as one of the complex structures. Yeah, so there is, it's not unique one-to-one, so there is, you have more freedom. Yeah, so the upshot, maybe just very roughly, which is how I'm going to see this, the hyperkähler geometry of M is somehow controlled by the complex geometry of, let's say you fix one complex structure, you make it into a compact complex surface, then you study the holomorphic geometry of that compact complex surface and how it varies and so on. Yeah, so that's my point of view. And so once you'd say that, the thing an algebraic geometer would ask, okay, in a different formulation is, I mean, how many different ways are there to make this real four-manifold into a complex surface? So how many complex structures are there on this real four-manifold, and how many means how many different, and then an algebraic geometer would say, is there a modular space of K3 surfaces? This means a geometric space where each point corresponds exactly to one biholomorphism class of these compact complex surfaces. And that's like one of the final goals of algebraic or complex geometry, if you start with one projective variety or Kähler manifold, is to ask, is there a modular space? Can you construct it? What is the geometry? And so the way to describe this is to consider families. So for this, that's just a definition. A family of whatever, but in our case K3 surfaces, is a proper submersion of complex manifolds. So the total space is this curly X, usually base will be B, such that each fiber is of the type that you want is a complex K3 surface. I'm not claiming that all of them need to be different. They could all be the same. You can take the product family. But eventually, a moduli space would be a space where such a family exists, and any other family is obtained by a fallback procedure from a universal family via a map into the moduli space. Yeah, and one example are twistor families. If you take a hyperkähler metric on your K3, which exists, as I said, you construct the twistor space, which is a very specific family over P1, yeah, with fibers K3 surfaces. And what are the K3 surfaces appearing there? These are exactly the K3 surfaces that you get if you take M, comma, I don't know, I'm running out of letters, N, where N is one of the complex structures in the two-sphere of G parallel complex structures. So that's the twistor family, and it's very rare that you have a family over a compact base. Yeah? So that's usually hard to construct, and that's why complex geometers like the twistor construction. Okay, if you want to study all these complex structures and all these families, you maybe ask yourself, what is the topology of M if M is underlying a K3 surface? And there is a theorem which says that all these surfaces are deformation equivalent. It means that there is only one K3 manifold. There is only one differentiable four-manifold underlying all these surfaces. So the differential topology is fixed. And you're really only varying the complex structure that you put on the same thing. Yeah, and this also means you can compute the topological invariance. And very important is this H2. And this is 3 abelian of rank 22. And then you have even, you know what the intersection form is. In classical notation is this. This just means, for us, the most important information is that the intersection product will have signature 319 on this Z to the 22. So that's non-degenerate, but indefinite. Yeah, so the symmetry groups that will appear will be something like SO319. Okay, and then once you have the topology, you somehow, if you're given a K3 surface, you have to somehow rigidify and model, okay, this will have this topology, but it's just diffeomorphic to this, so you fix one isomorphism on the level of cohomology. Yeah? So this is called a marking. Now given an X, you mark it, you don't write, okay, you can write a diffeomorphism to this M, but the only thing I will remember is the induced isomorphism on the topological level. And that's then together, this gives a marked K3 surface. And why do I do this? Because now I can use Hodge theory to write down something very explicit, and in the end it will be projective geometry inside some specific projective space. Yeah, so this is the idea of the whole project, is to somehow study the interaction of twistor family or twistor theory with period maps, which you use to study any sort of family, let's say, of projective manifolds. You can write down the period map. Sometimes it tells you a lot, sometimes not. In the case of K3 surfaces, it stores almost all the information. And so what do? Once you know that your topology is like a Z22 on the integral level, you also know the real and the complex, the topology with real and complex coefficients, so you tensor with R and C. And once you have this a K3 surface where you mark the cohomology, you can map any cohomology class to the specific model. Yeah, for example, you have the holomorphic 2 form, which will be closed. So it will give you a class in cohomology with complex coefficients. So you move it to the model, and then since this is only determined by up to scalar, you go to projective space. Yeah, so for any K3 surface, you compute the holomorphic symplectic form, get the cohomology class, you move it to your identification to the model, and then you get a line, and that's a P21. Yeah, if you choose coordinates, it's a P21. Okay, and then you see relatively easily, because you're on a surface, that if you intersect this thing with itself, this class, yeah, I mean, the wedge product of two holomorphic forms is a holomorphic 4 form, which will not exist on your surface. So that means that you get a relation that the symmetric extension of your intersection product to your complex vector space will be 0. This means your image of your period point, this will lie in a quadric. Yeah, this is a quadric equation given by the holomorphic extension, or the complex linear extension of this signature 319 form. And on the other hand, if you take a holomorphic symplectic form and you wedge it with its bar, it will be positive. And that's another condition which tells you that you will lie in some really Euclidean open part of your quadric. Yeah, and that's a very concrete thing. And the interesting thing is, which makes the whole theory start, that if you have a family, which is the thing that you want to study, and somehow individually you assign for each fiber, okay, you have to make sure that the identification is somehow in a continuous way. You assign this point here. This will give you a holomorphic map from the base of your family to the period domain. So that's somehow Griffith's theory in the 60s. Okay, and the main point is, if you have a twistor family which lives over P1, then you will get a holomorphic map from P1 to your quadric, let's say if you're an algebraic geometer, or it will even lie, so it will lie in your period domain. And that's something you like to study. It's a rational curve. So for each twistor family, you will get a rational curve in the quadric. Okay, and you know more about it. I already drew what I write in the first point here. Actually, this P1 is not mapped to a point. It's not, not mapped 2 to 1 or 5 to 1 to something. It's an embedding. Yeah? You really find a P1 inside, which means that essentially all the complex structures on this P1 are essentially different, up to maybe discrete things. And you can even write down the image, and this is maybe something you will like, in terms of an intersection of your quadric with a very specific plane. So the projectivization of a 3 space. And what is this 3 space in your C to the 22? If G is the hyperkähler metric that you use to construct the twistor space, then this will have self-dual 2 forms. I hope my signs are right. And there will be 3 of them. And this will span a 3 plane, which projectivize will give a plane. And then your P1 will be a conic in this plane. So now you can somehow get excited about classical, somehow algebraic geometry, but that's like the connection to, let's say, self-dual or anti-self-dual geometry. You remember the cohomology classes of the self-dual 2 forms. Yeah, in this. And okay, maybe it's not so clear that this completely describes the geometry, but it will. So at least locally, so this is an old theorem of Andreotti and Weil, if you take the universal deformation of a K3 surface, so this means that is a space which is 20-dimensional, you can compute, smooth ball, where there is a family of K3 surfaces, and this is all you can do when you want to deform the fixed complex structure in the middle. Then the period map associated to this universal deformation, once after you mark it, is a local biholomorphism at the base point. Yeah? So this means that, let's say I have a point here, which is the image of one of K3 surface. This quadric has the right dimension, right? So this quadric is a hypersurface, it's in P21, so it's 20-dimensional. Okay, that's an open subset, so the dimensions match. So there is a 20-dimensional ball here, which is a very concrete model of the universal deformation space of this X, which a priori is an extremely abstractly constructed space. Yeah? So in particular, this means that there are no obstructions to deforming a complex structure. It just means that there are no singularities in this deformation space. There are no directions which are there infinitesimally that you cannot move into. Right? In a manifold, if you have a direction, you can walk into this direction and there is a path. Yeah? So this theorem allows us to move towards our goal of constructing a space containing any K3 surface. Right? So if I have one of them, there is this universal deformation space, 20-dimensional. I map it to the period domain. I have this concrete model. And then I have to glue this stuff together because something which is a deformation of surface A might also be a deformation of surface B. And then I have to identify with universal properties. I do this. But of course, what happens, what will always happen if you glue stuff. You will get something non-House stuff. Yeah, you glue 20-dimensional balls together. And in the end, you end up with something non-Hausdorff. Yeah, so this is what is called the fine moduli space of marked K3 surfaces, or Burns-Rappaport domain, by a famous paper of Burns and Rappaport. And the construction I gave you was done by Beauville, and this is why I call this Beauville construction. There's a famous example of Atiyah, which shows that really this is non-Hausdorff, where you write down 2 families over punctured disk, which both extend to a family over the disk. Outside of the origin, these 2 families are isomorphic, but then in the origin you get to have 2 limits. Yeah, you approach the origin from 2 sides, you get 2 limits, typical non-Hausdorff behavior. Okay. So twistor cycles have played a decisive role afterwards. So we have this, this map. Yeah, so here's this abstractly glued space. It has this map to the period domain, which is very concrete. I want to study it. Todorov used twistor cycles to show this map is surjective. So every point in the period domain occurs as the period point of some K3 surface. And actually on each connected components, there are 2 of them. There's just a ±1 issue. And then the famous Burns-Rappaport paper describes the fibers of this map. This is locally biholomorphic map, although one should be very careful with intuition. As I said, this thing is very non-Hausdorff. So locally, this map is biholomorphic, but then the fibers are discrete, but it looks very strange. Namely, it's generically 2 to 1, or on each connected component, it's even 1 to 1. But then on special fibers, they will be infinite. But still, if each connected component is connected, this is just because it's non-Hausdorff, that the usual intuition as a covering is somehow completely misleading. Yeah, and there is a very specific way to understand the fibers in terms of the complex geometry of the K3 surface. I will not go into this. It's completely controlled, understood, but it's extremely complicated. Yeah? Okay, so the key takeaways are the moduli space of marked K3s is non-Hausdorff. This concrete model, which is somehow contracting this discrete information coming from the different markings, is nice, but there is this difference which is in the discrete fibers, which are hard to control. Okay, now you remember that in the end, in the beginning, I wanted to say I want a space where each point corresponds to a biholomorphism class of K3 surface. Yeah, so what does this Burns-Rappaport theorem tell you? Well, okay, here are pairs x, phi. So a point here is a K3 surface with a marking, but somehow the fibers with this map just have to do with the marking. In particular, if I have two K3 surfaces, I mark them, and they are mapped to the same point in the period domain, they are abstractly biholomorphic. However, this biholomorphism might have nothing to do with the marking, which is the point. So I'm in a situation that I introduced the marking to get concrete picture, but now I have to, in some sense, get rid of it again in order to go from isomorphism classes of marked K3s to biholomorphism classes. So I take the equivalence relation of differing by a marking. Yeah, so this is what I wrote. Changing the marking is actually realized by a very nice group. Yeah, essentially it's the orthogonal group of a lattice, or concretely you write down SO319, and then you take the integral points, and then there is an index 2 subgroup related to spinor. I mean, you have to, okay, spinor norm 1 elements. Yeah, so but that is a group of matrices which acts abstractly here, but very concretely on this picture. There is a representation of SO319, namely the vector space you started with, and there the gamma acts and by change of matrix, and it acts on this picture. So what you want to do, okay, there is something missing. So in the end, you want to take the quotient here, and eventually that's the same as taking the action on this concrete model and taking the quotient. I think you have 1, but this action is extremely wild. Yeah, it's extremely chaotic and ergodic, which means that, okay, in some sense, positively, any K3 surface after changing of marking is very close to any other. And this has been used in the theory a lot for positive results, but for us it's a dramatic statement, because this quotient here is some information coming from Lie theory. In the end, it's not even locally Hausdorff. It's even worse than this space, which locally is a ball, so Hausdorff, and only globally non-Hausdorff. This quotient is even locally non-Hausdorff. Yeah, so why is that? Because you can write down this omega concretely as a homogeneous space. You take the connected component of SO319, and then you compute the stabilizer of one point here in good coordinates. It's easy to see that this is SO2 times here this hyperbolic group, SO or Lorentzian, SO0119, which is non-compact. Yeah? And then you take a discrete subgroup here, and you let it act from the left, and then you have this non-compact subgroup, and that's the reason why this action is extremely wide. Yeah? So this is not even locally Hausdorff. However, as a Lie theorist, okay, if you say, tell me you have this non-compact subgroup in this group here, the reflex is to look for the maximal compact subgroup. Okay, every one of you can compute the maximal compact subgroup of SO319. It's 03 times 019, and then you make sure that the determinant is still 1. Yeah? So essentially it's this. And then you take any point in the period domain, or you take the point in the period domain you use to compute this stabilizer here, and you move this point just with the maximal compact subgroup, And since this is not the stabilizer, something will actually happen. If the stabilizer would have been the maximal compact, this would just fix this point. But at the moment where this is not the maximal compact, something will happen. The point will be moved. Okay, it's clear that you take a compact real Lie group, that this will give you a compact real submanifold. But the Lie theoretic magic is that this is a compact complex submanifold. And the point is, you have already seen it. It's actually the image of the twistor line, or one twistor line for one well-chosen scalar class that we already know. Yeah? So that's the magic. The magic is that this maximal compact group has a complex orbit, and it is exactly coming from this embedding of one twistor line. Yeah? Okay, and that's the start of somehow the positive results. Yeah? So the moment that you think you can despair and stop because everything is so bad, if you look for the reason, you'll find a possible thing to study, maybe with some positive outcome. Okay, and that lets me move to part 2, which is somehow moving in the direction of twistor vibrations. Yeah? So the main diagram somehow is this. Yeah, you have that we've encountered. We have a twistor family. It is over P1, and this P1, let's say as C0, is embedded in this period domain. Okay, as a complex geometer or algebraic geometer, whenever you see like a rational curve, say in a quadric, you want to deform it as a submanifold. Yeah, and you know this from, let's say, twistor theory. So this means you want to consider the Kodaira moduli space in which this submanifold is a point. Yeah? And for this, you compute the normal bundle and the cohomology. Yeah? And it's easy to compute the normal bundle because this is an intersection of a plane with a quadric. Yeah? So this means that there is an O2. So it's 19 copies of O2 on a P1. So the cohomology of this is 0, which means that the deformation is unobstructed, and you have 57 dimensions. Okay, that's one computation you would do if you see this picture. Yeah, so this means the Kodaira domain moduli space, which I call, because as a complex geometer I have to do this duad of omega, where this is a point, is of dimension 57. Actually, somehow you get another idea how to deform this, and actually it's a very good idea. I said that this twistor line is an intersection of the quadric with the plane. Just by linear algebra, you could also start just moving the plane, the free space, yeah, the free space in your C22. So that would be a Grassmann manifold. Yeah, and actually, so if you restrict to Grassmann planes, so free spaces, which are positive definite with respect to the Hermitian extension of the product that you have, then you get an open embedding of this part of the Grassmannian into your duad space, and any twistor line will be contained in this open set. Actually, but it's bigger. So the duad space is bigger than this, but this gives a good, already quite large neighborhood. Okay, so on the other hand, so I now studied basically this right-hand side. You can just look at the twistor space, which is a compact complex 3 manifold, as you know. Okay, it's never scalar, but at least in this case here, but it's fine. You can compute the abstract deformation theory of this. So unfortunately, or maybe good, you see that the obstruction space here is an H2 with values in the tangent bundle. This is non-zero. So you cannot just say this will move unobstructed. However, you can show by some harder work that nevertheless the abstract deformation space of this is smooth, and also of dimension 57 at the base point. Yeah, and then you think this cannot be a coincidence, and actually it isn't. And it is explained by the following. Yeah, okay, so this is now maybe the most technical slide. So I draw a picture. Yeah? So I said that my basic picture is this. I have P1 or C0. Yeah, I have F, a twistor space. Okay, I'm missing one dimension. Yeah, so it's three-dimensional, two-dimensional fibers. And this is embedded into omega. Yeah, so I can do a third thing. I now discussed how to deform this embedding. I have discussed a little bit how to deform this total space as an abstract complex manifold. You can set up a deformation theory for maps. Yeah, so where the objects are maps from X to Y, and then you ask yourself what would be a deformation of that. Well, that's relatively easy to write down, but hard to control. You would deform the total space, you would deform the base, and then you require that there still is a map from, at each point from the deformed thing at time t to the deformed thing at time t down here. Yeah, and formally, this is what I wrote down here. Yeah, a deformation of a family of K3 surfaces, which is this is the middle thing, which is over there. It's a curly x0 to c0 over the base b is, something even bigger. X goes to curly c goes to b, such that if I fix one point in the base, I get a picture like this for each point in the base. Okay, you already see that formally this is complicated and geometrically also hard to control. However, here in the end this will be fine. Yeah, I introduce one more piece of notation. I call this a second level family. If actually here, I did not specify this, but it's clear that in the end I want the base always to be P1 because I'm interested in start with a twistor family which is over P1. Any other thing I want to look at should have a vibration over P1. Okay, in the end you cannot move P1 because the complex structure is rigid, but let's just do this. And then you need markings, which is, you can ignore. Yeah? So whenever, I will draw a picture on the next slide. Yeah? So I call such second level family embedded if there exists a marking such that if I go to this middle, if I forget about the B, forget about the B and you just have a family, curly X, F to C, and I said for every point here, the fiber needs to be a K3, so I can just forget that this fiber is over B and assign the period point here. Yeah, so I have a period map going from the middle, C, to the period domain, and I just ask it to be an embedding if I restrict it to any of the P1 fibers that I have in C. Okay, and if I have such a thing, I can do, I get a map from the base B to the Kodaira moduli space. Yeah? So maybe I explain this in pictures. Yeah? So this is what a deformation of a family looks like. I have B. For each point B in the base, I have a curve over it, which is a P1, but this is not necessarily a trivial family here, but in the end, abstractly, each fiber is a P1. Over each P1, I have a free manifold. Yeah? This free manifold is fibered into K3 surfaces. These are the green ones. And so you have, let me draw the section which I have. Yeah, this is how this maps. Yeah, so this means that this green things are the fibers of this second map when restricted over the curve. Okay, and this moves. And so now I look at this in comparison to the period domain. And here it is. There is the period domain inside the quadric. Yeah, if I restrict to this green, to this red P1, I have K3 surfaces over it. It's marked. So for each, let's say, green point here, I have a point in the period domain. So in summary, I get a P1 in the period domain. And now, if I go to any other point B prime, I have this thing here, and it will be mapped to a different P1. So if I move along this B, I will get a family of P1s embedded in the period domain, and that's a family of cycles, and this will give you a map from the base B to the Kodaira moduli space, or the Dua-D space. And it's even the space that parameterizes, that subspace space which parameterizes smooth rational points, smooth rational curves. Okay, that's the situation. So the main point is now to study this map from B to the Dua-D space here. Okay, and actually, there is a local Torelli theorem which tells us that the situation is as nice as for individual K3 surfaces, and it tells us that this observation about the dimension was not a coincidence. Actually, you use this theorem here to prove that these two dimensions are both 57. So there is, I start with any twistor space, say X. Yeah. Then, as I said, you can consider this as an abstract 3 manifold, complex 3 manifold. This has a deformation space. Yeah, so you just deform this as an abstract manifold. However, this is the first sentence, the map to P1 will automatically deform with any deformation that you do with forgetting the map. Yeah? So you start with a twistor space, you for a moment forget this map, you deform this 3 manifold slightly, but then this deformation will again have a map to P1. Yeah, so this is what you have to prove. And this means that the universal family can be made into a second level family in this language I introduced, but the main point is to say there is automatic, you carry the fibration along. Yeah? And actually, if you carry this along, then this second level period map from the base of the universal deformation to the Kodaira moduli space is a local biholomorphism, which means that the deformation space of the total space, which is 57 dimensional, is locally isomorphic to the Kodaira moduli space, which was also 57 dimensional. And this is how you prove this, and this is how you prove that the deformation theory of the total space of the twistor family is actually unobstructed because the deformation functor of such maps is unobstructed. Yeah, so that's the technical definition. Yeah, so other way of saying this, for people who like functors, if you look at the deformation theory of f from x to P1, you can do two things. You can forget about f, so forget, you just deform x. I just said that anything I do here will lift here, and that's actually an isomorphism. On the other hand, I have this second level period map, which I explained. This will map to this extremely concrete space. Yeah, you should consider this as most abstract and this as most concrete. And the period map is also gives you an isomorphism to the deformation just of this embedded P1 in the period domain, which was realized by just moving a free plane around. Yeah, so and this I think it's a very good this is very good news. Okay, the upshot of this discussion is deforming the twistor space is the same as deforming the fibration in the category of fibrations. Abstractly is equivalent to deforming the corresponding twistor line inside omega by just moving a free plane. Now, I'm not saying that if I move the free plane a little bit, I can write you down the equations for the deformed map F, but somehow looked at all of it, I mean, that's just good enough. Okay, and this is so now I do the same thing. I glue, this was local deformation theory, now I glue everything together over the Kodaira space, over the space of rational curves inside the period domain, this is omega. And I get a complex manifold, so actually this time the gluing gives something Hausdorff. Yeah, so I improve the situation massively. A complex manifold that is a fine moduli space for marked total spaces of embedded families of K3 surfaces, which lies locally biholomorphically over this, this open, say, over a part of the Grassmannian. Yeah, so what does this mean in terms of twistor theory? So this means that there is a manifold, 57-dimensional manifold, maybe a lot of connected components and so on, where each point corresponds to a free manifold which is fibered into K3 surfaces. So this looks like one part of the datum that you need for a twistor space. Yeah, you see, I ignored other parts of the twistor construction. I just focus on, I have a free manifold fibering over a P1. Yeah? And I have a space which parametrizes such things, plus a marking. Yeah? I need the marking to, you see, always need the marking to move to the concrete situation. Yeah? However, this time, yeah, this is like the propaganda now. On this side, all the problem has disappeared. All the problems have disappeared. If I now look at the action of my gamma, which of course still acts by changing the marking, yeah. So how does it act? I mean, here in this picture, it's very easy to see. You have a point which is you have a cycle which is a point in this parameter space of cycles. You just move it physically with the concrete matrix action by gamma, and it gives you another cycle, and that's the new point, and that's the action on the parameter space of cycles. And this is actually properly discontinuous. Yeah? So this means that the quotient, you can take the quotient, you get a complex space with finite quotient singularities as a quotient, and then this means that this time you can even forget about the marking again, and this means you have a coarse moduli space for total spaces of such fibered freefolds. No? So coarse moduli space means there is no universal family, but this just means that every point here corresponds to one biholomorphism class of such a thing. I would call this maybe potential twistor spaces, yeah, because I'm just considering one part of the data. Yeah, so this time, so I think maybe for complex geometers this is not so interesting, or okay, maybe you have to convince them that it's interesting. But I mean, I think for people here, it's somehow maybe more clear that this is an interesting space, because it's a space where each point gives you something which could be like a twistor space of some geometric structure on your 4-manifold M. Okay, this brings me to part 3, which is concerned with the geometry of this cycle space. So the geometry of the space where each point corresponds to such a thing, and the relation to complex hyperkähler metrics. Okay, I recall where we are. Yeah, so we start always with the twistor family marked, so that I can map to the period domain. Then I had this the image inside the period domain, which was here this green thing. I consider this, let's say, as a point in the Grassmannian of positive 3 planes, which was sitting in this 2D space, and which you can show if you go to the connected component, which is also contained in the Grassmannian of 3 planes. Yeah, so, but it contains other planes which are not necessarily positive definite. Yeah? Okay, since this action is properly discontinuous, you can remove a certain subset which has not appeared yet, but plays a decisive role in the Burns-Rappaport theory. But you will recognize, I think. So in this geometry here, you have some, or in this projective space, you have some hyperplanes, linear hyperplanes. Yeah, so difficult to draw. Okay, I just draw this, and what is this? P of delta perp. Yeah, so what is delta? So this is now like a root system. Okay, you have this lattice, yeah? So this is your h, your z to the 22 with this very specific quadratic form. Then you look for things that square to -2. So where you plug it in twice and you get -2. And okay, there are many of them. And then since you have a non-degenerate form, you can look at all the vectors which are orthogonal to this. You have one point, you look at all the vectors orthogonal to that. It's a hyperplane in C22, and you projectivize to go to projective space, and that's my picture here. This will intersect the period domain. And actually, if you move these around with the group gamma, this will be dense. However, these things create problems. Namely, if you think, I just say this, it's not clear from what I said, it has to do with curves on your surface which cap to 0 against the Kähler form, which of course is not allowed to happen. Yeah? So one wants to remove them. So I'm just saying that if you remove all the points in this parameter space, which corresponds to curve, which actually lie in such a hyperplane, which does not seem possible, but okay, this has dimension 20 again, and this is a curve. So you might have your plane, your free plane that you use to intersect to be contained in this delta perp. It's completely possible, but you don't want those, and you remove that, and that's actually a closed analytic subset. And the reason is that this action that moves around these deltas is properly discontinuous. And so that's the interesting thing, and the relation to twistor theory is, if you look at all the points in the parameter space, this cycle space, which come from all possible twistor families that you constructed using the hyperkähler matrix coming from Yau's solution of Calabi conjecture. So really the real, honest hyperkähler matrix on M. Then this is this space. Yeah, so what is this space? You take one of those, and it's clear that if you take the group that is acting here, SO0319, you just move this curve around in the period domain. You will not leave it because this is homogeneous under SO319. It's just one orbit. So you get other examples of cycles. And if you remove those in the D, then you have all the twistor cycles. I mean, that was somehow well known. So the picture that you have to keep in mind of the Kodaira moduli space is this. So I start with the family that I constructed after 7 minutes with Yau's solution of the Calabi conjecture. I have this orbit in the space of cycles of this group, which now, interestingly, this is the side remark, that's a Riemannian symmetric space. So it's the Riemannian symmetric space associated to this group. Okay, this is the whole thing. And then I remove this D. Yeah, and so the set of twistor lines is the green thing minus the orange thing. And this looks like a linear subspace arrangement in this Riemannian symmetric space of non-compact type. The intersection actually has real codimension 3. So this is, if you want to read about this, there is a chapter in Besse's Einstein manifolds that describes this. Okay, and so that's how this space looks like. So each point here in this green thing corresponds to a real twistor line. However, that's a new result proven by us, that you cannot just say that if I fix a point here, there is a twistor family over the corresponding P1 in the period domain, but you can do this simultaneously along the whole green thing, and not just along the whole green thing, you can move a little bit in the complex direction. So there exists a unique gamma equivariant marked second level family, so that these were objects like this over C over U, over a gamma stable open subset containing the twistor lines, such that for each point actually lying in the twistor line subspace, the fiber that you get is the twistor family corresponding to this line. Yeah? So this is how this roughly looks like, this gray thing. Yeah, so it's actually known that if this point here in this cycle space, it characterizes the hyperkähler metric uniquely up to the action of gamma. So there you can say something like, is the twistor family coming from the hyperkähler metric corresponding to this point? Because that's well defined. And the theorem is that you can put all of these in a family. First over this, maybe one word about dimensions. So this green thing is totally real inside the whole complex manifold. Yeah, so this Riemannian symmetric space is real. The real dimension is also 57, and it's a complexification of that. Yeah? And you can do this, and so you have this U, and over this U you have a family of P1s. Okay, that's more or less by definition because they are in the parameter space of the P1s. But that on this family of P1s, you find a family of K3 surfaces which has this property. okay, that's, I should say that somehow the existence of this family over this green thing was, let's say, described in a survey article by Ryoichi Kobayashi in conference proceedings from 1990. But okay, I mean, our construction is really in terms of the Burns-Rappaport paper, and somehow it's not using differential geometry and some statements which you claim to be easily proved by the reader and so on. So maybe, okay, maybe this green family was kind of known, but okay, there is you prove that it's real analytic and then it extends into the complex direction. Okay, so up to this point, I was talking about this picture, yeah, and I said this is somehow, anything that looks like this is a potential twistor space, but I'm ignoring like 3/4 of the twistor datum, yeah? Because, as you know, they have additional structure, yeah? On this fibered 3 manifold, there is more stuff. Yeah, you need also P1s with normal bundle O1 plus O1, yeah? So, and okay, from my point of view, that's not for free, yeah? So that's an important part of the construction. And you have a relative symplectic form on the fibers, yeah? So formally it's a section in the relative 2 forms over P1 twisted with O2. Yeah, so I think most of you know. And so the proposition is, and that's, okay, that's not so hard to prove, because now the deformation theory of this is again controlled by this, and you compute. And you use old theorems of Kodaira, which was, okay, this is an approach which was, okay, I will give the reference soon, maybe known. Not only this one, but also this 2 and 3, they deform over this U, at least after shrinking of U. I mean, okay. Yes. No. So that's, I mean, the point is that, okay, that's somehow, I think in the old days, because of this normal bundle, I think Kodaira calls this stable or co-stable submanifold. So I mean, it just deforms. I mean, I have a family and it deforms sideways. Yeah? And this is basically open. Okay, so this means that, okay, go back. Over this U, also the other datum, except the real structure, survives in the deformation. Okay, it's not surprising to you that if I tell you, if I'm looking at such a point and I look for the directions into which the real structure deforms, it's exactly the green direction. So everything is completely as it should be. Okay, so, and then inspired by something which was done early on in the theory, for example, in this paper from 1983, you then use the original, and okay, for a long time, like until 10 years ago, I was worried what to do then. But then I learned that, you know, in the beginning of twistor theory, there was no real structure. Yeah, and for me, this was like the best news ever, because this meant I didn't have to think about, okay, what do I do if there is no real structure? You use just the original nonlinear graviton construction in this relative setting, yeah, to show the following theorem, that this deformation of the family induces a joint deformation of all solutions of the Calabi conjecture considered as Worth, and that's a little bit of a, you have to think a little bit how to formulate this correctly, as a complex hyperkähler matrix on the complexified tangent bundle of the real thing. I can comment on this, yeah? So what does this mean? What are the objects I get for any point C parametrized by U? There is a non-degenerate complex symmetric bilinear form on this, on the complexified tangent bundle of the underlying 4 manifold with holonomy. I mean, okay, once you have this, you run the whole Riemannian geometry standard package. There is a Levi-Civita connection. With holonomy group is SL2. Okay, it's hyperkähler geometry embedded into SO4C. And so this means that there is a sphere of parallel complex structures. And you see, that's the right place to look for complex structures on M. These are endomorphisms of the complexified tangent bundle. And if you compute this sphere of complex structures, they're all integrable. So this means that if I fix one of them, I get a compact complex surface. It will be a K3 surface. I compute the period map, and in the end, I get back the cycle. Yeah, so somehow this means that this gives an answer to the question, which was actually why I started this project with Martin Schwald long time ago, that, okay, it's clear that K3 surfaces lying on a real twistor cycle, they're not isomorphic, biholomorphic, but they share a common real hyperkähler metric. And somehow, then the question is, if you deform it a little bit, what is the relation between the complex structures given by the points on the cycle? And one answer is, there is this complex hyperkähler metric simultaneously taming all of them, such that this is the twistor family for this complex hyperkähler structure, and okay, everything deforms unobstructedly in the right dimensions, and at least now for small deformations, you have everything under control. Yeah? Okay, this is the end of this is the last slide, so maybe I can comment in the last 1 or 2 minutes why this is a good, these are the good objects. So there is only one problem. I mean, you could also get a family of complex also holomorphic hyperkähler metrics. Yeah? Because in the end, everything here is about complexifications. The only problem is that, right, if I have this M and I put it in some complexification, for example, okay, now I have to think. Right, if you think about the reverse Penrose construction, this is how you recover the hyperkähler metric from the twistor space. You go to the dual-D spaces of sections, which is 4-dimensional, and then if you have a real structure, you will have M embedded like this into the 4-dimensional Kodaira moduli space of the total space. Yeah? The only problem is with complexification is that they are not unique. They're only unique up to shrinking around M. And if you do stuff in families, if you have something which might shrink around M, it's very difficult to say something, it's a fiber bundle with fiber MC. Because if you try to glue stuff, something might have shrunken away, and since everything, the parameter spaces are non-compact, in the end everything might shrink to 0. So there is no uniform bound on the diameter of the complexification that you should fix. I mean, that's the only reason why I say I'm working on this compact 4-manifold. Of course, everything here is real analytic. If you fix a complexification, it will extend holomorphically as a holomorphic Riemannian hyperkähler metric on some small neighborhood. And the only reason I'm not saying that is the reason that I work relative to a non-compact base. For a long time, I tried to prove some uniformness, but I was not able. Okay, so I think I stop here and thank everyone for your attention.
Questions?
Do you have the result for higher dimensional hyperkähler?
So a lot of the deformation theory we have for any hyperkähler. The question of constructing moduli spaces, there is this problem that for hyperkähler, the Torelli theorem, the global is more complicated. And in the moment that the Torelli theorem is S for K3 surfaces, you can do everything. However, if in the moment where you have extra monodromy, anything related to fine moduli spaces, we don't know. And so, so some part is there. This latter part for the K3 surfaces, we just did for K3s, because there you need the moduli space and the universal family, because this is done on the universal family. So I would say, let's say 1/2 is for hyperkählers, and the breaking point is where global Torelli is used and where you need the strong form.
How about this deformation of the total family of Twistor?
The deformation theory is independent of dimension. Yeah, so this is So this is partly using, I mean, for K3 surfaces it's easier. I think it's using work of Eastwood on the Leray and so on. But I mean, this is for hyperkähler. So the fact that if you deform the twistor family for hyperkähler manifold, the F will deform with it. It's a computation of cohomology groups that is done by Brecan, Kirschner, and Schwald in all dimensions.
So, at what point did the non-housed Dolphins disappear?
It disappears when you pass to this parameter space of cycles. And the reason is, okay, somehow for differential geometers it's maybe not so surprising, because you see in the end, somehow for the real geometry, you're looking at the action of a discrete group on a Riemannian symmetric space with compact isotropy. So the point is somehow that by passing from the space to the space of cycles, you exactly move this one dimension. I mean, before the isotropy group was SO2 times SO119, and you move the 1 from the 119 to SO3, and then you get 19, you have somehow split signature, you separate the 3 dimensions, the positive ones and the negative ones, so in the end you have something definite. So I think that's where it's, and so somehow, if you look at, for example, Joyce's book on, there is this comment that he has something called hyperkähler moduli space and says, okay, this is more primitive and the actions are better. So in some sense, it was known, but I mean, the formulation was not in terms of cycles, it was in terms of metrics. And the whole observation is that there is an interpretation in terms of complex geometry where if you drop the totally real assumption, then you get some complex object, but it still has geometric meaning, and you can recover the actual Riemannian metrics as the real part of the whole theory.
Other questions? So if not, I see we have a couple participants online. So are there any questions on Zoom? Okay, if not, then let's thank speakers.
Thanks a lot.